Okay, everyone, assalamu alaikum. And hello, let's begin. We are going to start with our next concept in this topic, which is functions, and that's composite functions. All right, so that's what we want to do today. Composite functions. Now, I'll just begin in a minute. I'm just setting a couple things up. Walaikum assalam, Abdullah. Okay, everyone, let's start then. So we were doing functions. Now, until now, what we've done is we've talked about function notation, right? And then we talked about domain and range of functions, how to find range of a number of different types of functions. For example, linear functions, quadratic functions, right? We looked at all of this. Reciprocal functions or rational functions where you have x in the denominator. We've talked about these kinds of functions, how to find range of these functions. Then we talked about different types of relationships, one-to-one, many-to-one, one-to-many, many-to-many. Only the first two are functions, and inverse only exists for one-to-one functions. We looked at how the domain and range of a function and its inverse, how they are related. So domain of a function is the same as the range of the inverse function, and the range of a function is the same as the domain of the inverse function, and so on. We talked about how to draw their graphs, how their graphs are reflections of each other in the line y equals x. In the last session, we talked about inverse of quadratic functions, how to find inverse of quadratic functions. Now, quadratic functions are actually many-to-one functions. However, if you restrict the domain of the function in such a way that it becomes one-to-one, we looked at how we could find the inverse. Now, in this process, we first have to complete the square of the function and then make x the subject. And then when you take square root at the end, you would have plus minus. And then you have to decide whether to use plus there or minus there. How do you do that? Using the domain of the function that you're given. In this case, the domain was x less than 0. So we said x could only be less than 0 if we use a negative sign here, right? We talked about this in detail. We looked at a couple of other examples in this from the worksheet as well. We did question number 26 from the worksheet. We looked at all of these different parts. And we looked at question number 10 from the worksheet. These were two questions that we did in the last session, all right? And using these different parts of these questions, we learned a number of other things in the process as well. For example, this particular type of question, how to find the largest value or the smallest value of something for the inverse to exist. We talked about how to deal with that. But now we are moving on and starting our next concept, which is composite functions. Composite functions. Let's talk about this. Now, this is I think this is the most tricky part of this topic, the domain and range of composite functions. All right, finding composite functions is pretty straightforward, but there is just a 1 or 2 mark question that sometimes comes in which you have to figure out whether a composite function can exist or not. And sometimes when you have to find the domain of a composite function or the range of a composite function, that is something that's tricky sometimes. So let's try to understand that today. And then you should be able to do most of the questions from the worksheet after that. We will just be left with trigonometric functions. We will be covering them on Monday in the afternoon class, and then we'll have another class on Monday night in which we will do practice questions on functions. All right. And then on Tuesday after that, we could start function transformations, inshallah. Okay, so what are composite functions? First of all, let's try to understand that. Now, remember how a function worked. If you have a function f of x, and let's say that is equal to 5x plus 3. If you have a function like this, how does this function work? X is the input that you give to this function. So if you were to represent it using a diagram, it would look something like this. Now, this is really going to be important, understanding how the function works. So if you were to represent this function by this box f, what's happening is you're inputting something into this function, So x is going as an input to this function f. This function f is applying some operations on this input x. For example, in this case, what it's doing is it's multiplying the input by 5 and then adding 3 to that. And then it's giving you a result, which we call the output of the function, which is going to be f of x. So x is the input that goes to the function, and f of x is the output that you get from that function. Okay, now you could call this f of x, or you could also call this y, the output that you're getting. You could also call it this. Now, if instead of f of x, we had something else. So for example, if you had to find out, let's say, f of x squared minus 2. Now, what would that mean? F of x squared minus 2. This basically means the input to the function has now changed to x squared minus 2 instead of x. So now we are inputting x squared minus 2 inside this function f. Now, how would you evaluate something like this? F of x was equal to 5x plus 3. So if you had x as the input, the result was 5 into x plus 3. If you have x squared minus 2 as the input, what happens is x is replaced by x squared minus 2. So this expression would look like this: 5 multiplied by, wherever you have x in the function, you replace that with x squared minus 2. So it becomes 5 into x squared minus 2 plus 3. This is how you would evaluate an expression, a function like this, f of x squared minus 2. How do you evaluate that? Wherever you have x in the function, you replace that with x squared minus 2. And now you can simplify this, and that will give you 5x squared minus 10 plus 3, which is 5x squared minus 7. This is what f of x squared minus 2 turns out to be. Okay. Now, this is simple function notation that we understand already, how to input something other than x inside the function. But now let's say we have two separate functions. So let's say we have one function which is f of x. Now let me just write down a random function here. Let's say you have something like this: f of x, let's say that equals x squared plus 2x plus 5. You have something like this. And you have another function, let's call that g of x. And that maybe looks something like this. It's that same function, let's say, that we wrote above, 5x plus 3. G of x is 5x plus 3. Now, if I were to evaluate something like this, f g of x, this is what we call a composite function, f g of x. Now, what does this mean? How do we evaluate a composite function? That's what we want to understand first. So we have one function f, another function g. We want to evaluate f g of x. This is a We're doing computer science as well. You might have seen in computer science nested functions, right? One function inside another function. So we have a big function. Inside that, you have maybe a bunch of other functions. These are called nested functions, right? And computer science used to call them nested functions. In mathematics, we call them composite functions, which means you have one function and inside that function, you have another function. Now, this is f g of x. Let's try to understand how this works. We can actually write this as, if you have to evaluate f g of x, we would start by writing f g of x like this. That will make it easier to understand. We'll say it basically means f of g of x. So we introduce another bracket here, like this. And that basically means inside the function f, we have to input g of x. Just like earlier, inside f, we were inputting x squared minus 2. Now we're saying, instead of inputting x squared minus 2, put g of x inside f. All right, so now g of x is going as an input to f. So how would you evaluate this? You would say, okay, this now becomes f of g of x. Now what's g of x? G of x is this, 5x plus 3. So that becomes f of 5x plus 3. And now this is something that you know how to evaluate. So in place of x in this function, wherever you have x here, so you have x here and you have x here, you replace that x with 5x plus 3. So what does that become? That becomes 5x plus 3 whole squared plus 2 into 5x plus 3 plus 5. This is fg of x. This is how you would evaluate this expression. Make sense? This is fg of x, where we are inputting function g inside f. This is what it turns out to be. You could simplify this if you wanted to, or you could just leave it like this. It depends on what they're asking about. But that's the function fg of x. You could simplify it if you want, right? Now, similarly, we could evaluate gf of x as well. How would gf of x look like? Gf of x would look something like this. If we have gf of x, again, we could introduce another bracket between these functions like this. We could say it's g of f of x. So inside the function g, we have to input f. All right. Now, what's f? F is x squared plus 2x plus 5. So we say it becomes x squared plus 2x plus 5. And that's going to give us something. It's going to become 5 into, remember, this is the function g. Inside this function g, we want to input x squared plus 2x plus 5 instead of x. So it becomes 5 into x squared plus 2x plus 5 plus 3. That is gf of x. This is how you would evaluate gf of x. Now, you can see here, if it's not very clear, you could try simplifying it as well to understand that fg of x is not the same as gf of x. All right, they're not the same. So fg of x means you're inputting g inside f. Gf of x means you're inputting f inside f, f inside g. These are different functions. You could try simplifying this and this to understand the end results are going to be different. If you just evaluate the square term, you have 5x whole squared. The first one would have 25x squared, and the second one would just have 5x squared. So it's clear that they cannot be identical. They're different. So in general, this is true that fg of x is not the same as gf of x. All right. So in general, this is what is true. Now there's an exception. Exception is that the two functions are inverse of each other. If you have one function f, another function g, if they are inverse of each other, in that case, fg of x and gf of x would be the same, and they would actually be equal to x. But that's an exception. In general, what happens is fg of x and gf of x, they're going to be equal to each other. Okay. So this is how we evaluate composite functions. Now, this is one notation that you need to know about, fg of x and gf of x. There's another notation as well that you need to know about. Let me actually just copy these functions here again. These are the two functions that we're talking about. I'm going to just copy them here again. Okay. Now, another thing that you have to evaluate sometimes is something like this. Maybe you're asked about, let's say, g square of x. G square of x. Now, what would that mean? G square of x. Now, this is actually a short form of writing g of x. It's not the same as g of x whole squared. So these two are different things. If we have g of x and whole square of that, that's different from g square of x, right? These are two different things. So g square of x, what does that mean? That basically means g of x. How would you evaluate this function? This is also a composite function. It's a function like this that you're inputting the function g inside the function g. So what does that become? You could use so you have g of x like this, and then you could use brackets like this. You could say it's g of x. So inside g, you have to input g. What does that mean? What's g of x? G of x is this 5x plus 3. So it becomes g of 5x plus 3. Now, wherever you have x in this function, you input 5x plus 3. So that becomes 5 into 5x plus 3 plus 3. And that is g square of x. Again, if you wanted to simplify this, you could do that. It would become 25x plus 15 plus 3, that's 18. This is g square of x. G of x whole squared, on the other hand, is different. That basically means 5x plus 3 whole squared. And that basically gives you 25x squared plus 2 into 5x into 3, that's 30x plus 9. So this is different, and g square of x is different. You need to understand this notation as well. All right, so here as well, you need to remember g square of x is not the same as it's not the same as g of x whole square. G square of x basically means this thing. G of x. That's how we use it in function notation. Okay. Now you have done another notation earlier in trigonometry, if you remember. So in trigonometry, we used to say if you have sine square x, that was basically sine of x whole squared. Right now, it's just by convention. The actual mathematical form is this: sine of x whole squared. We write it in a short form like this, and from whenever we have this, we understand from this that it means sine of x whole squared. It's just how this short form is basically defined, right? So we have basically agreed that whenever we write sine square x, that would mean sine x whole squared. On the other hand, the actual mathematical thing is this: g of x. G square of x is just a short form of writing that same thing. So in function notation, we have a different convention, and we say, okay, when you have g square of x, that is not going to mean the same thing as g of x whole squared, but instead it would mean g of x. All right, so don't confuse it with what you used to do in trigonometry, for instance, with sine square x, cos square x, and tan square x. For instance, this is different. All right, g square of x would be g of x. Any problem with this? Any confusion?
No, sir.
No? All right, let's have a look at another example. Let's say you had to do something like this now. So instead of g square of x, let's say you had something like this. You had g square of f of x. What if you had something like this? G square of f of x. How do you understand this now? Now you have three functions. What are those three functions? This is g of f of x. So you have one function g, inside that you have another function g, and inside that you have another function f. All right, so yeah, it's a composite function that has three functions, that has three layers basically. Now, how do you evaluate this? You start evaluating this from the innermost function, because remember, x is the input. Which function is applying on x first? The function that's closest to it. F is the one that's closest to it. So what happens the first time is, we could use a bracket like this, and we could say, inside this function g, we have to input this function f. So it becomes g of f. What's f? F is x squared plus 2x plus 5. All right, so it becomes x squared plus 2x plus 5. All right, so that's the first innermost function evaluated. This is what we get from that. Now, what happens after this? Now we look at the next function that's applying. Now inside this function g, we have to input x squared plus 2x plus 5. Now, what was the function g? The function g, let me write that on the side here. The function g was 5x plus 3. 5x plus 3. Now, inside that function g, we have to input this thing. And that outer g remains as it is. Inside now, we're saying, instead of this x, input this thing. What does that give you? 5 into x squared plus 2x plus 5 plus 3. This is what we get inside. All right. Now, let's simplify this and see what that gives us. G into, in fact, G of, not into, it's not multiplying, G of 5x squared plus 10x plus 25 plus 3, that's going to be 28. And now we have the final step in which inside G, we have to input 5x squared plus 10x plus 28. Now, again, in this function, in place of x, we input this whole thing. So it becomes 5 into 5x squared plus 10x plus 28. And then you have plus 3 outside. That is the final result that you get from g squared of f of x. And that would simplify to 25x squared plus 50x plus 28 times 5, that's 140. 140 plus 3 is 143. This is the function g square of f of x. So if you had more than 2 functions like this, maximum that it would usually go to is 3. That's also kind of rare, but if it happens, this is how you would approach it. Does that make sense to everyone? How to evaluate composite functions? All right. This is how we find composite functions. Okay, so that makes sense. Let's have a look at one more example. Now, let's say you have something like this. You have a function of this form. Now, this is something that you'll also see sometimes in some of the recent past papers. Let's say you have a function that looks like this, 2x plus 3. And you have another function, let's call that g of x. And that function is maybe 5x squared minus 1. You have these 2 functions. All right. One function is f of x and the other function is g of x. And now what you have is, you basically have something like this. They have, let's say, given you, or in fact, before that, let's try this for instance. Let's say we have to find f inverse. This also happens sometimes. So I'll just give you this example first, and then we'll look at another one. Let's say you have f inverse of g of x. Let's say you have something like this. You want to find what this composite function would be. F inverse of g of x. Now, you know how to evaluate f of g of x. Now, what about f inverse of g of x? What would you have to do for that? First of all, you would have to find the f inverse function. And then inside that f inverse function, you would input g. Let's see how that would work. So first of all, you find the f inverse function. Let's see what that turns out to be. So f of x is equal to 2x plus 3. How do we find inverse functions? We say let y equals f of x. And that gives us y equal to 2x plus 3. Make x the subject. And that would give you y minus 3 over 2. And then f inverse of x, that basically becomes x minus 3 over 2. This is the f inverse function. All right. And now what you have to do is you have to evaluate f inverse of g of x. So now once you have f inverse function, what you do is you say, okay, f inverse of g of x, what does that mean? That means inside f inverse, you have to input this function g of x. So again, you can use brackets like this to understand this better. This composite function basically looks like this. Inside f inverse, you have to input g of x. So what would this become? F inverse of 5x squared minus 1. So inside the f inverse function, you have to input 5x squared minus 1. All right. Now, what does that give you? This is F inverse. Wherever you have x in this expression, you replace that with 5x squared minus 1. So this becomes 5x squared minus 1 minus 3 divided by 2. And F inverse of g of x, therefore, is 5x squared minus 4 divided by 2. This could be another type of composite function that you might have to deal with. This is how you evaluate this. F inverse of g of x equals 5x squared minus 4 divided by 2. Any problem with this? Any questions, anyone?
Sir,
Yes?
sir, I couldn't understand this. How did you inputted x minus 3 over 2 into 5x squared minus 1?
It's the other way around. It's F inverse of g of x. So we have to input g of x inside F inverse. What's g of x? G of x is 5x squared minus 1. That's here. So now what we are saying is inside F inverse of x, you have to input 5x squared minus 1. So basically, in that inverse function, wherever you have x, you have to replace that with 5x squared minus 1. So it becomes 5x squared minus 1 minus 3 divided by 4. That's what you get from this.
Okay, sir. Okay.
Okay? All right. Now, sometimes what also happens is you end up getting something like this. So they will give you an equation of this form. Let's say it says f of h of x that equals g of x. All right. They might give you an equation like this, and then they have given you what f of x is and what g of x is. So let's say f of x in this case is 2x plus 3. And g of x is 5x squared minus 1. All right. So they've given you f of x and they've given you g of x. And they've given you a relationship like this, an equation like this, that fh of x equals g of x. All right. Fh of x equals g of x. And now let's say they're asking you for the function h of x. You have to find what h of x is. H of x is defined like this. They're saying if you evaluate this composite function f of h of x, that would be the same thing as g of x. This is what they're saying. Given this, they want an expression for h of x. What would h of x look like? Now, how do we deal with problems like these? One way to do this is, that works for any question like this, using what you used to do in matrices. So if you remember matrices from O-levels, if you had something like this, if you had, for instance, a product of two matrices, A and B, and the result was equal to C. So if there were three matrices, A, B, and C, and the product of A and B gave you C, and now you were supposed to find B. Let's say A was known and C was known, and you were supposed to find B. How would you make B the subject in this equation? What you used to do was, you would multiply both sides by A inverse to get rid of this A. But now A is on the left side here, right? The first, on the left side, what you would do would be, you would pre-multiply A inverse, as in you would multiply by A inverse on the left side. And then you have A inverse into A into B. On the right side, you would do the same thing. It would become A inverse multiplied by C. And now on the left side, since you have A inverse into A, they're inverse of each other. They sort of get canceled out. It becomes an identity matrix. So it gets eliminated. And we're just left with B. B equals A inverse of C. So in matrices, if you remember, this is how you would approach it, right? If you had to get rid of this A and make B the subject, you would multiply both sides by A inverse. but you have to pre-multiply because A is on the left side here. So you'll have to pre-multiply A inverse. That means A inverse should be on the left side when you're doing multiplication. And that would make B the subject. It works kind of in a similar way when you have functions as well. Now, yes, f(h) of x does not mean multiplication as such. It's a composite function. So it's not exactly the same as matrices. But the logic works almost exactly the same way. Now, what do I mean by that? Let's try to understand this. We have f(h) of x. That equals g of x. We want to make h of x the subject. What we can do is, we can say, let's apply function f inverse on both sides. You have f here, right? If you apply function f inverse on both sides, on the left side, you would have something like this. You would have f inverse of f of h of x. And on the right side, you would have f inverse of g of x. So basically, you apply f inverse on both sides like this. Okay. And now, f inverse and f, they cancel out each other's effect, as an f inverse will be doing the opposite of what f is doing. So whatever they do, it basically just cancels out. So if f is, for instance, adding 3 to an input, f inverse would be subtracting 3 from the input, and you would get the same result back. So basically, they cancel each other's effect, and we are left with h of x. So if you have to evaluate h of x, you would say that's f inverse of g of x. So given these two functions, f of x and g of x, if you were given this equation, f(h) of x equals g of x, and you were supposed to find h of x, how would you do that? You would apply f inverse on both sides like this. H of x would then equal f inverse of g of x. And now you could just evaluate this composite function, which we just did before. This is exactly what we evaluated here, f inverse of g of x. So basically, if this equation was true, h of x would be this thing. That's 5x squared minus 4 divided by 2. That's what h of x would be. All right. Similarly, if you had something slightly different, for instance, you had something like this instead. So in this case, you had f of x and g of x. Let's say instead you had, or in fact, let's use the same two functions, f of x and g of x, and let's just change the equation that we've got. Let's use another letter now, f, g, h, I, j. Okay, let's have a function k of x. So let's say you have k. In fact, k is actually used as a constant generally, but it's okay. So let's say you have k of f of x, and that equals g of x. And we had to find the function k of x. So k is a function in this case, and k is k of x basically, right? So we're just using another letter, right? It should not confuse you as such. Just like we have f of x, we have g of x, we could have k of x as well. K is just the name of the function. Given kf of x equal to g of x, if we had to find k of x, how do you do that? Now you have f coming on the right side. In the previous example, f was coming on the left side. So what we did was we applied f inverse on the left, right, like this. Now, if f was coming on the right side, what you would do would be, you would not multiply, you would apply f inverse on the right side in both sides. So you'd say on the left side of the equation, it becomes k of f inverse of x, that equals g of f inverse of x. So on both sides of the equation, f inverse comes on the right side, right? So we have f inverse after kf, and we have f inverse after g here. So now on the left side of the equation, f and f inverse, they disappear, and we are left with k of x and k of x equals gf inverse of x. So if we had to find an expression for k of x in this case, what would that be? That would be gf inverse of x. All right, and that will give us this expression. Does this make sense to everyone? This is also something that you need to know. It's not tested that often, but it is tested sometimes. You'll see at least 2-3 questions on this in the recent papers. I hope this makes sense. All right. Okay. All right, good. Let's have a look at the domain and range of composite functions then. Okay, so now that we understand how to evaluate composite functions and how to find a function that is missing here using this equation, this is how the process would work. Now let's get to the more tricky part. Once you understand that, it's not that tricky after all, but it's just something that you need to make sure that you remember. Otherwise, it will be hard to figure out in the exam itself. Domain and range of composite functions. Let's try to understand what that is about. Now, this did not used to be tested a lot earlier, but in the recent papers, it has started coming quite frequently now. Domain and range of composite functions. Domain range of composite functions. And also identifying when a composite function can be formed or not formed. All right, we want to understand that. Now let's do that using the help of an example. With the help of an example, let's say we have a function f and we have a function g, and they look like this. So let's say we have f of x, and f of x is, let's assume, a linear function like this, minus 4x plus 5. And the domain of f of x is x greater than 0. Let's assume this is the domain of f of x. And we have another function g of x. And that is a quadratic function that looks like this, minus x squared plus 2x plus 2. And the domain of x, sorry, domain of this function g is all real values. All right. So there's no restriction on what you can input in this function. G of x could be any real value. Now, what you want to understand is, you want to understand, can function f g of x be formed or not? Can function f g of x be formed or not? Is it possible to form that function, or is it not possible to form that function? That is what we want to understand. Okay. Now, how do we understand this? For this, we first need to understand how composite functions are evaluated, how composite functions work. So we have learned how to find an expression for composite functions. For example, we know how to evaluate f g of x, we know how to evaluate g f of x. But now we need to understand how a composite function really works. What does the input go through in different steps of the process of applying this function? Let's talk about this function f g of x. If you have a function f g of x, what you understand it as is f of g of x, right? That's what we used to say. F g of x means f of g of x. All right. Now, when we write a function like this, what I'm going to do is I'm going to name these functions something to generalize this process. The function that you have outside here, I'm going to call this the outer function. So in this case, f is the outer function. And the function that you have inside here, the function that's coming afterwards, the function that is written on the second place, we're going to call that the inner function. Okay. So in f(g) of x, g would be the inner function and f would be the outer function. So if you had any other function, any other composite function now, for example, if you had m in m of n of x, n would be the inner function and m would be the outer function. If you had gf of x, in this case, f would be the inner function and g would be the outer function. So whatever function is coming first, that is the outer function. Whatever function is coming second, that is going to be the inner function. Now, how does this composite function work? How is this function evaluated? This x is the input that we are given to this function. Now, what happens to x first of all? So when x goes into this function as an input, how does this function work? So let's say we have this input going into the function x. What happens to x in the very beginning? What's the function closest to x? G. That's the function that's written close to x, g. So first of all, what happens is x goes as an input to the function g. Okay? X goes as an input to the function g first of all. That's the first thing that happens. All right, x is going as an input to function g. Now what g does is, g applies some operation on x and gives you an output. So g gives you some output. What is that output going to be? That output is going to be g of x. All right, that's what we get at the end, g of x. So x goes as an input to g first of all. So we're talking about f(g) of x function. In this particular function, what's happening is x is going as an input to g first of all. G gives you an output, that's g of x. And now once you have g of x goes as an input to the function f now. All right. So this g of x goes as an input to the function f. That's the second function that you've got. Now g of x is going as an input to that function. And now f gives you an output. F applies some operation on g of x and gives you an output. That final output is f of g of x. That's the final result that you get. This is how a composite function works, right? So this function f(g) of x, these are the different steps that this function would be going through. X would be going as an input to g, and then g would be giving an output, that's g of x, and then g of x will be going as an input to the function f, and f will be giving you this output, that is f(g) of x. Now the question is, in this case, given these two functions, f of x and g of x, we want to figure out, can this function, this composite function f(g) of x be formed? Is it possible to form this function? Now, how do you understand that? You see, first of all, x is going as an input to the function g. Now, what can go as an input to the function g? What's the domain of the function g? It's x belongs to real values. That means x could be any real value. All right, x could be any real value. So to this function, anything could go. So this input that you're inputting into g, it could be any input, right? That's what this function says. So let's write that here. The domain here is all real numbers. So this means x can be any real number, any real number. Now that is what is going as an input to the function g. Now, when this goes as an input to the function g, what does g give as an output? G gives you g of x. That's the output of the function. Now, this is a quadratic function. What's the range of this function? The output that this function gives, the y values, what can be the possible y values that you get from this function? They will be given by the range of this function. Now, can we find the range of this function? It's a quadratic function, minus x squared plus 2x plus 2. where x could be any real value. What does this quadratic function look like? What's the shape of this quadratic function? The shape of this quadratic function, g of x, it's going to be an n shape, right? So it's going to look like this. It's an n-shaped graph like this. We're talking about g of x. G of x looks like this. What's the range of this function? If the domain is all real values, that means the whole function is valid. The whole function is valid. X could be any real value. What about the y values? You can look at the graph. It has some maximum value. All right. So the range of the function would be anything less than that. So we'll have to find the turning point of this function. How do you find the turning point of this function? You could use competing square, minus b/2a differentiation, whatever you want to do. But using any method, what you have to do is you have to find the turning point of this function. Let's figure that out. X equals minus b/2a, minus b/2a, so that's minus 2 divided by 2 into minus 1. What does that give us? Minus 2 over minus 2, that's going to be 1. So x equals 1. What about the corresponding y value, g of x? When you input this back, x equals 1 into this function g, what does that give you? That will give you minus 1 plus 2, that's 1 plus 2, that's 3. Y value turns out to be 3. What that tells us is this turning point of g is 1 and 3. So what's the range of this function g then? If domain was all real values, what's the range of this function? If this is 3, we can say the range of g is y less than or equal to 3. That's the range of this function. So that means when you input any real value into this function g, the output that you get, it could be any value less than or equal to 3. It could be 3, 2, 2.5, 1.7, 0, minus 2, minus 5, minus 100, right? It could be any value that's less than 3. That's the range of this function, all right? Now, let me write that here. So what we're doing is we're saying we could input anything inside this function g. So as an input to g, you could have anything. What is g giving as an output? We just found that out. The output that you're getting from this is less than or equal to 3. So any value less than 3, that's the output that you're getting from. Now, what is the next thing that has to happen after this? What's the next thing that has to happen after this? Output that you're getting. I'm sorry, just a minute. Okay, so this output that you're getting from the first function, that is going as an input to the function f. And we have a condition on the function f that the function f can only take inputs that are greater than 0. So what's the domain of the function f? Domain of the function f is that you can only have values that are greater than 0. Now, let's write that down here as well. So g is giving you outputs that are less than or equal to 3, and function f can only take inputs that are greater than 0. Now, think about it. Do we have a problem? The problem is less than equal to 3 means it could be any value in the negative side as well. So basically, it could be any value to the left of 3. So if I had a number line like this, what happens is we're going to have 0 somewhere and 3 somewhere. The output that you're getting from the function g is basically anything to the left of 3. And the input that you can have from function, input that you can give to function f has to be greater than 0. That means this input, this is the output of g. We can say the range of g. What about the domain of f? Domain of f is anything to the right of 0. This is the domain. So this region is going to be negative values. And that is going to cause some problems because whenever g gives a negative value, f cannot take that as an input and function is going to break. And that's what happens in programming as well. So again, that computer science reference again, when you make a function and you have a composite function, a nested function, if the function that's inside gives you an output that the outer function cannot accept, the function breaks, you get an error and it stops working, right? That's what's happening here. When the function g gives you an output that is negative, which it can give sometimes. Yes, it can give some positive values as well. It can give 2, it can give 1, 1.5. But there are some possibilities, some cases in which the output is going to be negative. And the function f is not going to accept that. That means the function f g of x cannot be formed in this case. For the function f g of x to be formed, every single output that you get from the function g, we should have been able to put that in that function f. If we can't do that, then we have a problem. The function cannot be formed. Now, I hope that logic makes sense. I'm going to write down a statement here now, and then we're going to refer back to this using that statement and understand how we're going to remember this whole thing. So basically, the outcome, the result from this is that the function f g of x cannot be formed. Now, why can it not be formed? Because there are some values of g that we cannot input in the function f, because function f cannot take that as an input. Now, let me write that statement down, what you need to remember from this, and then we'll refer back to this example after that. So for a composite function to be formed, you have some condition, and that's this. A composite function f g of x. Composite function f g of x. This is just an example. F g of x can only be formed, it can only exist if the whole range that means the whole output of the inner function. What's the inner function here? In this case, it's g, is part of the domain of the outer function. And what's the outer function in this case? The outer function in this case, when you have f g of x, is f. So what's the condition for a function f g of x to be formed? A function f g of x, it can only be formed if the whole range of the inner function, is part of the domain of the outer function. Because if some part of the range of the inner function, any part of the range of the inner function, is not part of the domain of the outer function, when the value of the when the value of the inner function becomes that, the function is going to break and we're going to have a problem. The function f g of x cannot be formed. So what we have here is less than equal to 3. What does that represent? That basically represents the range of g, right? Less than equal to 3, that's the range of g. And what does this represent? Greater than 0. This represents the domain of f. Now this range of g less than equal to 3, all of this has to be part of the domain of the function f. In this case, that is not the case, because less than equal to 3 has some values that you cannot input in this domain. If you have this can also include negative values, and negative values cannot be input in the function f. So less than equal to 3 could also have negative values, but they cannot be input in the function f because f takes only values that are greater than 0. So for a function f g of x to be formed, the condition is the whole range of the inner function, the whole output of the inner function, you should be able to put that into the outer function. That means it should be part of the domain of the outer function. All right. Now, in the cases that you would get, you would just have something like this, that you would just be looking at this scenario, that if this is true or not, if the range of the inner function is the same as the domain of the outer function. These two things have to basically correspond. If they don't correspond, then we have a problem. Now, what that means is, if, for instance, range of the inner function was maybe y less than equal to 3, in this case, it's y less than equal to 3. Now, if the domain of the outer function was, let's say, all real values, this would work, right? All of this is part of all real values. This could work, right? So the whole range is part of the domain. If the domain was, let's say, x less than 10, that also works, because every single value that is less than equal to 3, that's also less than 10. So it satisfies the condition. So the condition is that the whole range of the inner function, it has to be part of the domain of the outer function. But mostly what's going to happen is, in the question that you get, if the range is y less than equal to 3, you would basically say the domain of the outer function would also be at least x less than equal to 3, right? At a minimum, it should be less than equal to 3. If it's less than equal to 2, for instance, that would not be acceptable, because then some values that the inner function is giving you cannot be input into the outer function, and that will be a problem. Okay, so you need to remember that these two things correspond to each other. What two things? Range of the inner function and the domain of the outer function. Okay, you need to remember this connection. These two things are connected to each other. Range of inner, domain of outer. Range of inner, domain of outer. Okay, so these two things have to correspond to each other if the composite function has to be formed. Otherwise, the composite function cannot be formed. All right. Now that's one thing that you need to know about the domain and range of composite functions. This is the condition for the composite function to be formed. All right. This is the condition that we have for that. For a composite function to be formed, this has to be true. Now, another thing is, you should be able to figure out the domain of the composite function from the domain of the inner function. And that works like this. If a composite function can be formed, in that case, let me write that directly. The domain of the composite function is the same as the domain of the inner function. So sometimes what can happen is, they might ask you to write down the domain of the composite function that you have found. What would be the domain of the composite function? The domain of the composite function is going to be the same as the domain of the inner function, because when you form a composite function, what exactly is happening? The input that you're giving, the input x, that's actually going to g first of all, which is the inner function in this case, right? X first of all goes to the inner function. So the composite function can take anything as an input that the function g can take as an input. All right. So whatever function g can take as an input, that's what the composite function can take as an input. So that's why we say domain of the composite function is the same as the domain of the domain of the inner function. So that gives you another thing to remember now, and that is domain of the inner function. That gives you the domain of the composite function. Now, this is what you can use to write down the domain of the composite function. The previous case, that's basically a condition for forming a composite function in the first place. This is the condition for forming a composite function. And the second thing is just how to find the domain of the composite function using the inner function. So whatever is the domain of the inner function, that's the same as the domain of the composite function. Okay, I hope that makes sense. Any problem with this? Any questions, anyone? Yes?
Can't we restrict the range like from 0 to 3 and 3 to 0?
How do we do that? How can we restrict the range of this function from 0 to 3 if the domain of the function is all real values? So in order to restrict the range of the inner function, we would have to do something to the domain of the inner function. And the domain in this case is fixed, right? So they've given us the domain already. Okay. So given that domain, the range is just less than equal to 3. So we can't really change that ourselves. Okay. All right, now let's have a look at one question quickly and then we end for today. Now, this is not from the worksheet. It's from a recent paper. I'll just copy it like this. Let's quickly try this and then we end for today. So we have this function f that is such that f of x equals 2x plus 3 for x greater than or equal to 0. So we have one function f, and that looks like this. F of x equals 2x plus 3. And the domain of this function is x greater than or equal to 0. And we have another function g of x, which looks like this. G of x equals ax squared plus b. And the domain of this function g is x less than or equal to q. Okay, we have these two functions given, where a, b, and q are constants. The function fg is such that fg of x equals 6x squared minus 21. So we have this composite function given as well. It's given that fg of x equals 6x squared minus 21. And the domain of that function is x less than or equal to q as well. Let me write that composite function here as well. Fg of x, this is given to be 6x squared minus 21. And the domain of this function is given to be x less than or equal to q. Even if this domain was not given, you should have been able to figure it out yourself. Why? Because if you have fg, what's the inner function? The inner function is g. What's the domain of the inner function? Domain of the inner function is x less than or equal to q. That should be the same as the domain of the composite function. All right, so you can see both of those domains are the same.
Sir,
All right. Yes.
sir, if f of x was the inner function, then the domain would be x greater than or equal to 0.
Yes, exactly. If it was gf of x, the domain of gf of x would be x greater than or equal to 0. All right. Okay.
Yes, sir.
Now, in the first part, it says find the values of a and b. Now, given this information, we need to find what a is and what b is. How can we think about this? We have f of x, we have g of x, we have fg of x given. All right, fg of x is 6x squared minus 21. Now, how do you find g of x? Now, one possibility could be what we just discussed some time ago. You could find g of x. How do you find g of x? You could do something like this. F inverse of f of g of x. On the right side, you would say f inverse of 6x squared minus 21. So you would get g of x equal to f inverse of 6x squared minus 21. You could evaluate this and then just compare it with that. You would get the values of a and b. That is one possibility. But in this case, I think it's easier to do it the other way around. They have given you fg of x. What you can do is you can find your own fg of x as well using the functions that are given. You have f of x, you have g of x. What you can do is you can find fg of x yourself. Fg of x. Let's find fg of x yourself from the information that's given. You have f of x and g of x. Just use that to find this function, and then you can compare it with what they have given. And that can give you the values of a and b. Let's try this. Fg of x is f of g of x. That means inside the function f, you have to input g. So that means it's f of ax squared plus b. So in the function f, wherever you have x, you have to replace that with ax squared plus b. And that will give you fg of x. Let's see what that turns out to be. It's 2 times a into x squared plus b plus 3. You can simplify this, and that gives you 2ax squared plus 2b plus 3. This is fg of x. Now, this is the fg of x that you can find from the given function. Now, they have given that this function is 6x squared minus 21. You can just compare these two results. You can say, okay, this is the fg of x that I'm getting. Let's compare it with what they have given. So they have given that fg of x equals 2ax squared plus 2b plus 3. In fact, we have found that fg of x equals this. Just compare these two now. What's the coefficient of x squared that we have? We have the coefficient of x squared as 2a. What have they given as the coefficient of x squared? They have given the coefficient of x squared to be 6. So we just compare the two. We say we are getting 2a, and they are saying it should be 6. If we compare the two, that gives us 2a equals 6, and the value of a turns out to be 3. That's the value of a. And similarly, you can see what the constant is. In our form, the constant is 2b plus 3. The constant is basically anything that does not have x, right? So this is the constant 2b plus 3. They have given the constant to be minus 21. Let's compare the two. We get 2b plus 3 equal to minus 21. And now the value of b turns out to be minus 24 divided by 2, that's minus 12. So a equals 3 and b equals negative 12. Okay, that's what we were looking for in the first part. So they gave us an expression for fg of x. We found our own expression, and then we just compared the two. All right, so a equals 3 and b equals minus 12. Let's look at the second part now. Now in the second part, it says, find the greatest possible value of q. Greatest possible value of q. Now what's q? Q is basically this thing, this number. G of x, x less than or equal to q. That's the domain of the function g. Domain of the function g. Now we need to find the greatest possible value of the function q. How do we think about that? That's the question. Greatest possible value of q. Now this is quite tricky. It basically uses the concept that we have just done. Remember when a function can be formed? So when a composite function can be formed, we have a function f of x, and that function is 2x plus 3. And we're given that the domain of this function is x greater than or equal to 0, right? And we have another function g of x, and that function is ax squared plus b. Now we know the values of a and b. A is 3, so that's 3x squared plus b, so that's minus 12. And the domain of this function is x less than or equal to q. That's the domain of this function. So we have these two functions, f of x and g of x, and we have the domain of the other function, that's x less than or equal to q. Now, we're talking about the composite function fg of x, right? For fg of x to be formed, remember what the condition is? What two things have to correspond to each other? Range of inner and domain of outer. That means whatever is the range of the inner function, all of that we should be able to put in the domain of the outer function. Now, what's the inner function? The inner function is g. So range of inner function. We should be input all of that into domain of outer function. Outer function is f. Now we know one of these things. We know the domain of the outer function. What's the domain of the outer function? The domain of the outer function is x greater than or equal to 0. So this is something that we do know. It should be x greater than or equal to 0. So what we can say is the range of the inner function, therefore, at the very least, that also has to be greater than or equal to 0. The range of the inner function, that means g of x, for the function g, y should be greater than or equal to 0 as well. Or the whole function g of x, that has to be greater than or equal to 0. Okay? Make sense? So what do we do now? We have the function g of x. All we have to do is put that g of x greater than equal to 0. What's g of x? G of x is 3x squared minus 12. That's greater than equal to 0. Take 12 to the other side, and that gives you 3x squared greater than equal to 12. X squared equals greater than equal to 4. That's an inequality that you can solve now and find the possible values of x that you get from this. So what did we do? We said for f g of x to be formed, the range of the inner function, all of that should be part of the domain of the outer function. All right. What's the range of the inner function? It's g of x. What's the domain of the outer function? It's x greater than equal to 0. We knew that already from the question. So from that, we figured out that the range of the inner function should also be greater than equal to 0 at a minimum. Okay. And that gives us g of x greater than equal to 0. That means 3x squared minus 12 should be greater than equal to 0. Now we can find the values of x from this. How do we solve this inequality? Remember quadratic inequalities? How did we use to solve quadratic inequalities? We would first need to treat this as an equation. Let's say x squared equals 4. We can't do this, remember. We can't take square root in inequalities because that will make it something like this. That's incorrect. We can't do it. We have to solve it the proper way. We treat this as an equation. Remember, we did this in quadratics. Treat this as an equation, get two values of x, plus minus 2. These are the two cutoff points, the two x-intercepts of this function. It's a U-shaped function. It looks like this. Sorry. It's a U-shaped function. It looks like this. We have found the two x-intercepts. One x-intercept is -2, the other is +2. We want this to be greater than equal to 0. Which parts are we looking at? This part and this part. That means x could either be less than or equal to this value or greater than equal to this value. We get two possible solutions, x less than or equal to -2 or x greater than or equal to 2. That's how we used to solve quadratic inequalities. All right, so we get either x less than or equal to -2 or x greater than or equal to 2. Now, what's the domain that they have given in the question? X less than equal to q. That's what they had given us. Let's compare it with that. Now, the form that they have given is x less than equal to q. So which one of these two is possible? The right one does not have any maximum value, right? That's going up to infinity. That's not the one that they're using. They're using the less than equal to 1. Let's compare the two. What do we get? The largest possible value of q, that can be -2. That's the value that we were looking for. That's the largest possible value of q in this case. Make sense? Now, for you to be able to figure this out, you need to absolutely make sure that you understand this very, very well. The range of inner function, you should be able to put that in the domain of the outer function as a whole. That's the condition for forming a composite function. All right. These two things correspond to each other. Range of inner function, domain of outer function. Make sense? That's the largest possible value of q. Let's have a look at the next part quickly. Now it says it's now given that that q equals -3. So now they have given the value of q that's -3. We found the largest possible value of q that was -2. They're saying now q is -3, right? It's less than -2. That's possible. So it's now given that q is equal to -3. Now you'll use that value. Find the range of fg, range of the composite function. Now, how do you find that? Part 3. Now, we already know the value of, we already know the composite function, fg of x. What was that? Composite function was 6x² - 21. This was the composite function. They have given us the domain of this function, x less than equal to q, and they're telling us that the value of q now is -3. So that means this domain becomes x less than equal to -3. This is the composite function. What we need to do is we need to find the range of this composite function, range of fg. Now, range of the composite function is found like any other function, right? Just treat this as a normal function, 6x² - 21. It's a quadratic function. We have the domain of the function. How do you find the domain? How do you find the range of quadratic functions? Just like you do it for any quadratic function, you do it here. So there's no specific method. There's no separate method for this. For finding the range of the composite function, when you have the domain, you just use that domain to find the range. Now, what does this function look like? It's a quadratic function. It's a U-shaped graph, right? It would look like this. Now, what part of this function, of this quadratic function is valid? Remember, for quadratic functions, you have to first find out the turning point. So let's find the turning point of this graph. Let's find the turning point and see what that looks like. Let's say this is what it looks like. Let's say this is the turning point. Let's find the turning point first of all. How do you do that? -b/2a, you could use that. And in fact, in this case, it's pretty obvious, but anyway, let's try this. -b/2a, what's b here? There's no b. Coefficient of x is basically 0, right? That's missing. So we could say x equals -b, which is -0 over 2 times 6. It's going to be 0 in any case because the x term is missing. So the x coordinate of the turning point is 0. What about the y coordinate? You can put this back in the function, and that gives you -21. So the turning point is 0 and -21. Where is -3 going to be? Is it on the left side of the turning point or the right side? It's on the left side. So it's going to be here. So the x coordinate is -3. And what about the y coordinate of this turning point? Sorry, not the turning point, of -3, corresponding to -3. If you input -3 here, fg of -3, what does that give you? 6 into 9 minus 21, that's giving me 33. So this is 33. The y coordinate here is 33. Which part of this function is valid? Towards the left of -3, that means only this part is valid. So what's the range now? What's the lowest point of the graph? This point, that's 33. What's the highest point? Well, there's no highest point. So the range, therefore, is going to be y greater than or equal to 33, right? Anything equal to or above 33. We spent quite some time on quadratic functions earlier on how to find range of quadratic functions. So it's a standard range question for quadratic functions. All right, that's the range y greater than or equal to 33. Okay. Now let's have a look at the last part now. That's the range of fg. Find an expression for fg whole inverse of x and state the domain of fg whole inverse. So now we need to find the inverse of this function, fg whole inverse of x. Part 4. So fg of x, that is 6x² - 21. And the domain is less than or equal to -3. That's the domain of this function. We need to find the inverse of this. All right. Now, we just treat it like any other function, right? So we have to find fg whole inverse of x. So the inverse of this whole function. So just use the standard process for finding inverse. Let's say let y equals fg of x, right? So it becomes y equals 6x squared minus 21. Make x the subject. Generally, you would have to complete the square for quadratic functions first. Now, in this case, you don't have any x term. So you don't really have to complete the square because you can just make x the subject directly. It will become this 6x squared equals y plus 21. X squared equals y plus 21 over 6. Take square root on both sides, but remember, whenever you take square root, we have to put plus minus. So it becomes x equals plus minus square root of y plus 21 divided by 6. And now you need to decide between plus and minus. Should you have a plus sign there or a minus sign here? Since the question says x less than equal to 3, that means this value of x has to be less than or equal to -3. Now, how can you get a value that's less than equal to -3? Can you get that value with a positive sign or a negative sign? A positive sign is going to give you something positive that can't be less than equal to -3. So we need minus here for getting something that's less than equal to -3. So what does that tell us? That means x is supposed to be minus square root of y plus 21 over 6. This whole thing is inside square root. And now we can write down the inverse function. We can say fg whole inverse of x, that is minus square root of x plus 21 divided by 6. That's the inverse function. All right. Now they also asked us to state the domain of fg whole inverse of x. What's the domain of fg whole inverse? Domain of the inverse function is the range of the original function. What was the range of the original function? We found that in the previous part. Range of the original function was greater than equal to 33. So what's the domain of this inverse function? We would say x is greater than or equal to 33. This is the domain of this inverse function. Okay, how do you find that? Domain of inverse function is the same as the range of the original function. So this should also be greater than or equal to 33. Does that make sense? Okay, so that's about composite functions. Make sure that you go through the notes again, maybe watch the recording again as well if you need to digest this well, because this is, I think, the trickiest part of this functions topic. This is how it works. All right. Now, tomorrow we will be talking about trigonometric functions and how to find range of trigonometric functions in the afternoon class. And at night tomorrow, we have an extra class. Sorry, not tomorrow. I mean, by tomorrow, I mean Monday. On Monday, in the afternoon class, we will be doing trigonometric functions, the domain and range of trigonometric functions, and also on functions. So I expect before that, you can skip the trigonometric ones for now. But apart from that, try the rest of the questions. All right. So that's what we want to do in the next class. So be ready for that. That's it for today. Those of you who are on YouTube, I have a past paper session starting on 13th April. The registration link for that is there in the description. So we'll be doing complete yearly past papers for paper 1, paper 3, M1 and S1 starting from 13th April. You can find all the details in the description of this video. Also in the live chat, you can see that comment highlighted. If you're interested, you can have a look at all the details in that description. All right. Okay, I'll see you again in the next class. Allah Hafiz. Yes, any questions? Did somebody unmute themselves for a question?
Yeah, sorry, your voice cut out while you were explaining the last part. When you were talking about the last part, not the question, like when you were talking at the end. Your voice cut out for a second. I don't know what you said.
Okay, so basically, I was just first of all, I was telling you about the Monday class. On Monday, we will be doing trigonometric functions, the range of trigonometric functions in our first class. And then we'll have another class at night on Monday. We will not have it on Tuesday. We'll have it on Monday instead. In that class, we'll be doing a lot of practice questions on functions. All right, so make sure that you do the complete worksheet before that. Apart from the trigonometric functions, you can do the whole worksheet. And if you have any problems, we will discuss them in the class that we have that day. All right.
Okay, sir.
Okay, great. I'll see you again in the next class. Allah Hafiz.